integration for the K12 education system. But before we get started, if you could just take a moment and just press subscribe, I would greatly appreciate it. STEM learning is generative. It's a revisionary process where students can grapple with their learning. They can take the scientific knowledge, the engineering knowledge, and then create something with the engineering design process, all while integrating mathematics and technology. STEM integration looks a little bit like this. I know it's a lot to look at, but take a moment and just look at the four areas. We have the scientific method or scientific methodology, the engineering design process, the technology landscape, and the mathematical practices. When you're looking at the scientific method, we're looking at the study of the physical world. What are the natural things that students should learn about, and how can they apply this knowledge into the next concept, the engineering design process? Now, engineering, there are concepts that you do need to learn about, but there's also the engineering design process where you can take the scientific knowledge and then apply that, creating something new with the design process. Then you have the technology landscape, the application of technology and engineering design, fully integrated. Now, we talk about pedagogy, which is the study of understanding how children learn, but how do children look at the engineering and design process and the scientific knowledge? It's a lot different than the way an adult would look at it. So we have to break it down into steps. And then how do we integrate the mathematical practices? And I don't mean just the computational math. What's the thinking behind the math? What's the thinking behind the science? And what does that look like when it's fully integrated? Because we believe sometimes that STEM is something, like I said, where you go or what you do, but it's fully integrated, because then they can take these concepts, the math concepts, the science concepts, the technology and the engineering concepts, and fully integrate them or transfer them to something else. Distinguishing characteristics of STEM integration. We have the practices of engineering and engineering design. And again, this is where students learn about engineering. What is the design process? What's the problem that they're designing, or what concept are they designing? What are they going to do with it? What model are they creating, and what that structure and function is? So what's the structure and what's the function of the design that they're creating? And then we have the anchor science standards and mathematical discipline. We are really looking at what science knowledge is going to be needed in order to create that engineering design, and then what thinking needs to happen behind the mathematical practices in order to help develop the design. And then 21st century skills. 21st century can mean a lot of things, but I'm going to go with how are we using technology in order to advance what we're doing, and not just, for example, social media or a presentation, for example, like what I'm doing. I mean, are students able to develop something that's three-dimensional, for example? Doctors today can use a three-dimensional design before they do surgery. They can scan the entire body and practice using 3D augmented reality goggles or glasses and do the surgery before they actually do the real surgery. So that's 21st century skills. So what are we doing to give students access to those 21st century skills? And then what's the real world problem or task? Now, I just gave you an example of one, but it could also be global warming. Maybe there is a catastrophe and you need to send some type of technology in order to remove some waste. Maybe it's waste that is very harmful and it's radioactive, and you need to send in some type of robot. So you need to understand what that science is, the radioactivity, a little bit about the periodic table, and then will this contraption or this robot that you need to send in to pull it out be able to withstand that radioactivity, for example. So the next thing I want to touch on are the next generation science standards. I'm not going to go into full detail with the next generation science standards, but I want to touch on what the next generation science standards want students to know and what teachers need to help students learn. So the first thing are the science and engineering practices. The next are the disciplinary core ideas, and then the cross-cutting concept. Those science and engineering practices really look at how those two integrate, again, the natural world, the world we live in, and then also understanding that engineering design, and then the disciplinary core ideas. Those core ideas can be life science, they can be physical science, they can be earth and space science, and then the engineering practices, and then the cross-cutting concepts. How are we getting students to think about their learning? Is it a stability in motion? Is it a cause and effect? Are we looking at the parts of something? So just a quick overview of what the next generation science standards are. Here's one example of one of the next generation science standards. Now, this standard actually can be performed or created and provided for students in elementary, middle, or high school, primary or secondary. And this standard is motion and stability, also called the performance expectation. This is what we expect students to be able to do and know by the end of the learning process. So plan and conduct an investigation to provide evidence of the effect of balanced and unbalanced forces on the motion of an object. Then we have these science and engineering practices. So the science is balanced and unbalanced forces. That's the natural world. And then you have the engineering design. So design something that actually demonstrates the forces. That's the full integration. Then we have the disciplinary core idea. We know that the discipline in this situation is physical science. Then we have the cross-cutting concepts. We're looking at stability, probably more like middle or high school or secondary. And then we have cause and effect. So students will be able to see what's the cause and the effect of the unbalanced and balanced forces. And then we have the mathematical or mathematics application, the mathematical practices. So make sense of the problem and persevere through it. Are students giving up, or are they persevering through it? Are they making use of the structure, of the function, attending to precision, critiquing the reasoning of others? Are they talking to each other about this process? And are they modeling with the mathematics? As an educator, the first thing you can do is start off with a story. The story could be a video. In this situation, it could be about flight in space. It could be about stability in motion. It could be about the unbalanced and balanced forces. It could be about Newton's laws. Now, that's the scientific knowledge. And then you have the design process. What structure and function are students going to create in order to demonstrate that they understand unbalanced and balanced forces? Again, very elementary, but middle and high school could start adding the mathematics that goes along with understanding this. So if this was an elementary school, I would be looking at cause and effect. I would want students to understand what the unbalanced and balanced forces are. What's drag? What's gravity? What's lift? What's thrust? And then I would actually have them draw a diagram. That's mathematical practices concepts. Are students able to see what that looks like in a two-dimensional object, and then even a three-dimensional object, and then have a conversation around that? And in that conversation, I would be looking at, are students having meaningful conversations around the structure and function? I'd be listening for that. And are they confused? Are they using the scientific knowledge that they learned about in that video or that article or in that book? And then what's the integration of tech and mathematics? And then what's that full capstone project? Capstone meaning end project. It may not happen in a week, but maybe by the end of the school year, students will be able to talk about it if it's a bigger picture project. And then when we really are looking at what activities are students doing? What's the teaching that's involved? What's the learning that's involved? What's taking place? How are you teaching as a teacher, and how are students learning the content and skill? Why are they learning the concept and skill? So is there vocabulary that they need to know? Are students talking to each other? When students talk to each other, they are more likely to put this concept into their long-term memory. Now, as an educator, by the time I got to fifth or sixth period, I was great at it. But if I wasn't letting students talk about it, I was just doing the stand and deliver or the sit and get situation. Let your students talk about it. Let them revisit it over time. Don't just do it once. Do it over several weeks, and even revisit it even if you move on to a new concept, because typically there's something that's integrated with that. And then what's the project? How will students use the knowledge to create that project using the design process? And then the problem. How will students use the knowledge to answer real world problems? And I know that's big picture, but it's certainly something that students can do. And they can use this information whether they decide to go into any STEM career. They can use it if they're going into the political arena. If they are voting, they will understand these concepts if it's talking about global warming. So just a little bit of the big picture, and I will be going over this in some new upcoming videos. So remember, take a moment, subscribe, and come back at least once a week for more updated information around the next generation, science standards, and STEM full integration in the classroom.